Welcome to the November 4th edition of our ME Research Seminar here at South Dakota Mines. Today we have Dr. Song, who's a collaborator of Dr. T, and he's at the University of Hawaii in Manoa, but presently in Seattle. But so he's going to talk about his research and have some time for Q&A. So there's welcome, Dr. Zhang, talking about navigation and ocean flows and autonomous vehicles. All right, I'll hand it over to you. Thank you.
All right, thank you very much for the nice introduction, and thank you again for hosting me. So I know it's kind of challenging, attending a talk that with the speaker is away. So I'll keep monitoring the chat box here on Zoom. So if there's any questions from the audience there, we can probably discuss the questions in more details after the talk. So today I'd like to talk a little bit about the ocean, particularly navigation in ocean flows. So I know this is probably a subject area that doesn't come up quite often in South Dakota, but as we all know, ocean is very important no matter where we live. So we'll call that the Earth is a blue planet, and that is because ocean is the key to Earth ecological diversity and stability. And also it regulates the global climate on all sorts of scales. And most importantly, it affects both the island, the coastal, as well as the inland populations. So one of the important contribution of the ocean is to our economy as well. So this is one of the recent study done by World Wildlife Fund in 2020. So they estimated the assets that our global ocean is providing to the economy, global economy. And they were including the direct output of the ocean and also the carbon absorption by the ocean, as well as transportation and marine life overall, and tourism, and all aspects that ocean are participating in. And if you add all of them up together, and if you consider ocean as a economic group, and it actually ranks at the 8th largest economy body. So this is a very obvious evidence that no matter where you live, an ocean always plays an important role in your life. So although ocean is that important, our current understanding of the ocean as a whole is still very limited. So if we look at the traditional or conventional ways of sensing the ocean, so there are these following 4 methods in general. So the first one is using ocean observation satellites. So these satellites provide very valuable data of the surface layer of the ocean, and particularly the air-water interface. And that's where a lot of the weather phenomena occurs. But the limitation to that is also it can only provide you observation from the surface. In terms of getting data that is underneath the surface, there are these many different options. The most popular one, or the most costly one, I would argue, is probably by using a surface research vessel. So these vessels typically carry different sorts of sensors that are bottom facing, and it can penetrate water column as far as a couple thousand meters. And the downside of this large campaign style ocean observation is that it's quite costly. So as you probably realize that scheduling such a observation mission takes a lot of time and logistic effort. And also the operational cost, not only in dollar amount, but also in manpower, is also daunting. So that's why we can't just simply rely on this research vessel to map out the entire ocean body. And another type of ocean observation instrument is this static seafloor mounted sensor platform. So these sensors are typically statically mounted on the ocean floor, or sometimes on the coastal line, or sometimes even anchored or moored on the ocean surface. And these sensors, they can provide 24/7 observation of the water body. But the downside is that they have a very limited, spatial resolution. So because they cannot move around, and in their initial deployment, that also costs a lot of money and manpower. And also one major challenge is with getting the data offloaded from these sensors, collecting the data from these remotely located sensors. And that is also a very challenging task as well. And lastly, there's this emerging technology called floating drifters. So this is a particular artwork of the Argo floats, which we now have about 4,000 of them floating in the ocean. So these floating type of drifters, they can park themselves at a certain depth of the ocean, typically around 1,000 meters, depending on the type of floats that you are using. And they can drift with the water. And as it drifts, it samples the water column and then resurfaces after that sampling period. So as you can imagine, that the only controllability on this drifter is the depth. So it has no horizontal controllability. It has no propulsion that allows it to steer its orientation. So that leaves these drifters more or less dominated by the ocean current. And in that sense, they lack sampling efficiency. So usually scientists report that their drifter got trapped into eddies that they are not very interested in. And there's a lot of issues with having a lot of these floating infrastructures in the ocean, and how do we collect them, and so that we can prevent from pollution that are caused by the battery on these instruments. But the Argo project is arguably one of the most successful ocean observation projects so far, and it's about to grow significantly, not only in the number of floats that we're deploying, but also on the depth that these floats can cover. So now I want to talk about the role that robots play nowadays in ocean observation. So I like to call it robotification. So we have seen this trend most recently in almost all aspects of our daily lives, ranging from transportation, healthcare, food delivery, and shopping experiences. So ocean observation or ocean science is not an exception. So as a matter of fact, the robotification of ocean observation started about 60 years ago. So this is the photo of the SPUR-V, which is called the Special Purpose Underwater Research Vehicle. And it was first developed by Applied Physics Lab at University of Washington in 1957. So this vehicle is arguably the first autonomous underwater vehicle that is designed to sample the water column in the more or less controlled and intelligent way. So since then, there has been a lot of different underwater robotics platforms introduced. And one of the most popular ones, probably this torpedo shape bluefin 21 foot. Well, they call it 21-foot vehicle here. So you see that there is different form factors of these underwater vehicles. And one of them is this the Freedom vehicle representing the ROV type of style. So ROV representing remotely operable vehicle, which means that these vehicles are typically connected with the onshore operator through a tether, where a tether can communicate data or maybe transfer power as well. And on this bottom right corner here, which is the most sophisticated entry-level ROV that you can purchase nowadays. At only $2,500, you can buy this blue ROV2, and you can do a lot of fun stuff with it. So there are also some more exotic form factors of underwater robots. So this one is designed by Houston Mechatronics. It's called the Aquanaut. So it can actually transform its shape. So when these two half hulls close together, it resembles an ROV type of vehicle, and they can open these two half hulls and exposing these manipulators and cameras and whatnot. So this one is more like a snake, is initially designed by the NTNU, and it's called the Illume. So this vehicle is probably a very unique category that it stands alone on itself. So there are many ROV styles out there, which is definitely not an exhaustive list. And you probably have seen many of this in some of the mainstream movies. As a matter of fact, this Illum was just featured in a major movie, a Norwegian movie, just premiered last week. So if you're interested, you can check it out. The English name of the movie is called The North Sea. It's more like a disaster movie. So with all of these robots, they quickly become an important player in ocean observation. So as you can see, here is a table that was initially put together by Nelson et al. In 2015. And I modified it a little bit to add in some visual aids to represent the different type of vehicles and what type of skills, both in time and spatial skills, that they can cover in terms of ocean observation. As you see that they cover a very wide range and a very diverse resolution of ocean observations. But then the question is, how come we still don't see a lot of them running about, right? So we've seen almost like a revolutionary transformation of transportation provided by self-driving cars. We've seen a lot of drones nowadays. Is almost like a normal scene now, but there's still a very limited number of underwater robots out there. And as a matter of fact, most of them are still on the shelf, meaning that we don't typically operate them on a day-to-day basis. Right? So then what are the challenges and the bottlenecks are preventing a large-scale adaptation of this robot? So that's basically where my research focus resides in. So in order to talk about the challenges that these robots are facing, it's important to understand the properties of the ocean and how those properties are influencing the operation of the underwater robots. So first of all, the ocean is opaque to radio frequency communications because it is filled by seawater. So I was a little bit surprised that most people don't realize it, but if you go underwater, you would not be able to use Wi-Fi or LTE, or even most of the radio frequency communication needs. So that also means that if you submerge underwater, you will no longer be able to communicate with a satellite. So you cannot use GPS for your localization. And secondly, the ocean environment is very unstructured and mostly poorly instrumented. So that being said, if we deploy underwater robot in the ocean environment, it will not be able to see a lot of features like this, like what the self-driving car would be interacting with. So, but more likely, we'll be seeing almost nothing around it. So this is a figure that where Hui deploys their underwater vehicle for polar science research. So once the vehicle deviates from the sea level, it doesn't see much. Most of the feature around it is a fish every now and then, and mostly just water around it. So these two properties of the ocean together poses a challenge to the localization of these underwater robots that we're using. So as anybody who works in the field of robotics, we understand that localization is one of the major prerequisites for mobile autonomy. So in order to make decisions for control, path planning, we have to know where the robot is currently. So this is one of the major challenges that we're dealing with in the underwater robotics community. And a third challenge or a third property of the ocean is that it is a highly dynamic environment filled by perpetual ocean currents. So this is a rendering of from NASA that is visualizing the topple layer of ocean current. Although this current, the diversity of this current patterns start to degenerate a little bit as you go deeper, but these currents are still always around you, right? So this feature constitute another challenge that are posed to underwater robot, which is path planning challenge. The reason for that is when you deal with this small scale underwater robot comparing to their conventional large scale manned vehicles, and these vehicles tend to become very limited in terms of their actuation and sensing capabilities. And more often than not, their actuation is more or less dominated by the fact of background flow. So many times they drift with the ocean current and they cannot directly just fight against those ocean current. So there's a lot of challenges to do path planning so that we can do efficient sampling of the ocean with a limited amount of power and communication available on the vehicle. So many of my research has been focusing on these two challenges. And there's another bonus challenge that I will also quickly address towards the end of the talk, which I'm going to talk about later. But first of all, let's talk about the challenge with underwater localization. So to understand why there is such a challenge, let's first think about what are the goals of localization. So the goal of localization is to maintain an accurate estimation of the robot states in the reference coordinate frame. So these states typically comprises of the position and oftentimes also the velocity, sometimes acceleration as well, orientation, and some other states of the robot. If you're dealing with a robot with different type of sensors, sometimes the sensor has a drifting bias, and you might want it to estimate as well to be able to arrive at a constant, consistent localization performance. So with that, there are two key elements to localization. The first one is the existence of this reference, whose location, quote unquote, are known to the robot at all times. So I'm going to circle back on the meaning of these quotation marks because not all localization references were utilized for their locations only, okay? And the second key element is the capability so that the robot can measure its states relative to these references. So imagine if you're holding a map and navigating a campus or a new city. So the map will essentially be your reference, but you still should be able to take relative observations with respect to a certain building or a certain landmark to be able to find out your location with respect to these localization references. Okay, so now that we understand what are the key elements of localization, let's take a look at how we are addressing underwater localization challenges up to now. So most of the underwater localization solutions can be summarized by these couple of solutions here. Let's go through them one by one. The first one is resurfacing every now and then to receive GPS correction. So when the vehicle is operating close enough to the sea level, the vehicle typically will have a sensor called inertial navigation system. So what it does is basically using its accelerometer and gyroscope to measure its acceleration and angular velocity and deduce its future position based on its current position. So this process is called dead reckoning, right? So nowadays we have a lot of personal electronics that does just that. Our phones, our smartwatches does that reckoning the whole time. The issue with this dead reckoning approach is that since you are integrating this acceleration or angular velocity signals, any measurement noise, which is always existing, will also be accumulated over time. So to give you an example, if you use your accelerometer and gyroscope on your iPhone to perform directing localization, so after about an hour, your localization estimation will drift about 1 kilometer, right? So that's a very substantial localization noise. So you have to every now and then correct this accumulated localization error caused by this directing process. So when a vehicle is navigating around the water level, so the vehicle can go up to the water surface and talk to the satellite to localize its position using the GPS signal, so that you can keep the localization error bounded that way. So this is one type of localization method for underwater localization. And another type is probably the most dominant and popular one is by using these localization beacons, and mostly are acoustic beacons that emits acoustic signal broadcasting its location that is known to the beacon itself. So sometimes the beacon is moored on the surface. Sometimes the beacons is carried on the surface vessel that can have access to GPS. And sometimes you can install beacons on the seafloor if you are dealing with a confined project region that you are constantly going to perform underwater operation within. So if these vehicles are close enough to this beacon, it can perform bi-direction underwater communication between these the vehicle and the beacon to figure out where these vehicles are with respect to these acoustic beacons. So depending on the separation between these beacons, and there are different categorization of this underwater localization strategy. So LBL stands for long baseline localization. That's when your beacons are separated very far apart. And there's another technology called USBL, which stands for ultra short baseline. That's when you have beacons that are very close to each other so that they can be packaged together into a single sensor package. And by calculating the phase shift from the acoustic signal received from the underwater vehicle, you can essentially track the position of these robots. So the downside of this beacon-based technology is that, first of all, you have to deploy these beacons, right? And as you can imagine, it's very different from a GPS system because the ocean is inside out, right? So if you want to deploy beacons everywhere, that requires a lot of beacons to begin with. And secondly, the deployment and maintenance of these beacons is prohibitively expensive, right? So this also limits the range of these underwater vehicles to be to be within the proximity of these beacons. And there's a new type of underwater localization technique if the vehicle is close enough to the seafloor. So SLAM is a technique that is firstly originated in the robotics community, where it allows the robot to simultaneously localize itself, and in the meantime, create a map of its surroundings. So it's simultaneous localization mapping technique. So when the vehicle is close enough to the seafloor, it can physically use a camera or sonar system to measure features that are existing on the seafloor and create a map of this seafloor, and using that map to localize the vehicle itself. And if the vehicle carries a sensor called Doppler velocity log, which measures the relative vehicle velocity with respect to the seafloor, you can provide a direct velocity correction of the robot. So you have some bounding on the localization area, but since you lack global localization reference, you still cannot perform long duration navigation just using a DVL. Okay, so but this again constrains the robot to the proximity, close proximity of the seafloor. So the vehicle cannot go beyond somewhere between 200 to 300 meters away from the seafloor. Okay, so if you look at all of these existing methods, unless you have an unlimited budget to purchase very high accuracy navigational sensor, which is typically not available for these small scale robots, there isn't any possibility to localize this robot persistently if the vehicle is operating within this middle depth column, which can range on average somewhere between 1,000 to 3,000 meters on average. So that leaves a void in the ocean column that prohibits the vehicle, from exploring and collecting data from. So basically, there's no existing solutions to do long-term mid-depth navigation. Then the question that I was posing is, can we utilize the predictability of the ocean flows for navigation? Because when the vehicle travels in mid-depth column, the water current is always around the vehicle. And that's probably the only feature that we can leverage. And can we use flows to do navigation? So spoiler alert, the answer is a yes. And as a matter of fact, if we go back in time and think about how the ancient Polynesian voyagers discover islands, including the Hawaiian Islands, and hopping in between islands without any assist from modern technologies, they were actually using the fact that ocean currents are predictable to do their navigation. So here's a picture that shows a 62-foot long double hull canoe, which is called a hokulia. It's a canoe that was produced to repeat the sort of navigation that ancient Polynesian voyager conducted in the old days. And the canoe essentially traveled around the world in 2017 without any aids of the modern navigation technologies. So here's a photo of the master navigator Noah Thompson, so who is currently the acting president of the Polynesian Voyaging Society here in Hawaii. And so he was essentially trying to measure the sun at the time of sunset to set a course for the sail. So there's a lot of clues that these voyagers use in the old days to help them with their navigation. So a lot of them include reading the sky, so which includes the position of the stars. And here's an example of the star charts that are memorized by the master navigators, and where they can, based on the location of the stars in the clear sky at night, to find out the course that they need to set their canoe to. And during daytime, they can observe the position of the sun. But if in cloudy weather that you cannot see the sun or the stars, these voyagers, they learn how to read waves and swells so that they can inform themselves to understand in which direction the water is pushing their canoe into. And here is a photo of the a navigator is trying to read the swells and trying to identify the location of a remote island, and also the relative course of the canoe with respect to the direction that they are trying to go to. So very interestingly, there are a lot of other features which I'm not going to be able to list here. So one of the most interesting one that I found is actually the sea marks. So there's a lot of sea marks that these voyagers use as well. Flock of fish and schoolfish and flock of birds are also among these sea marks. So in the morning time, if you see a flock of birds in the middle of the ocean flying into a certain direction, that usually indicates that in the opposite direction of the travel direction of this flock of birds is where the island is at, because the birds goes out to prey in the morning, and they return back to the island at night. So you can use that as a clue to find out where the islands might be located. So clues like that are being leveraged by these Polynesian voyagers. And underwater vehicles can potentially also use these sort of clues to guide their navigation. But how do we do that? So let's take a look at the details here. So recall that we mentioned that there are two key elements to localization, the reference and your capability to measure with respect to this reference. So if we're using ocean current for navigation, we need to be able to understand ocean current or be able to forecast or predict these ocean currents ahead of time. So which is available. So ocean current circulation models already can provide forecasts of these ocean currents for up to 10 days. And there are models that can do way beyond that time. With a spatial resolution of 10,000 meter, 100 meter, or even smaller if you are talking about a regional model. And with a spatial temporal resolution, which is under an hour, or sometimes even shorter. So, okay, so we can establish a map of the ocean current. So what about measuring the flow speed on the robot? So this is a sensor called acoustic Doppler current profiler. So what it does is it meets acoustic signal, and it tries to measure the reflection of that acoustic wave bounced by the particles that are suspending in the water. So if you assume that these particles are traveling at the same speed as the ocean current, so then you are efficiently measuring the Doppler shift of the ocean current with respect to your acoustic source. So imagine that if the vehicle is carrying such a sensor, then we are able to measure the ocean current around the vehicle. And this ocean current speed is not disturbed by the vehicle's motion, because this sensor provides volumetric measurement, and this distance can be as far as 300 meters, somewhere between half a meter to 300 meters, depending on the sensor that you are using here. Okay, so but there are some important considerations that we needed to think about before we start to design such a localization algorithm. So first of all, it's something you probably are wondering. So there's a scale difference between the scale at which these ocean prediction models are predicting the ocean currents at versus the scale that the vehicle is traveling within, right? So typically these ocean models can predict on the spatial scale hundreds or thousands of meters and the temporal scales of hours. As a matter of fact, if you think about long distance traveling that can span for days or months, and usually if you are only relying on that reckoning, the error will exceed way beyond this resolution scales of the ocean prediction, which means that if you are dealing with long-term navigation, information provided by this course information becomes very critical and important to your navigation. So this can provide a reference to this long-term navigation. And secondly, there is a coupling relationship, because if you are measuring the relative flow velocity, so these ADCP are carried by these underwater vehicles, and what they are measuring is the relative flow velocity. So we still need to know what is the flow velocity in the inertia frame to be able to use this flow map, because the flow map is constructed based on the flow velocity in the inertia frame. So this means that we need to know the velocity of the robot itself to be able to transfer this relative observation into the inertia frame. So this is not a problem, because many of the underwater robotics localization strategy already estimate the velocity of the robot, right? But this creates a layer of coupling. And as a matter of fact, this layer of coupling plays an important role in the convergence of these underwater localization methods, which we're going to talk about later on. And lastly, the map that we're using right now is background flow velocity map, is a vector map that is highly ambiguous. So what I mean by that can be seen from this figure here. So if you look at these two vectors, they are very, very similar. So if you have a flow velocity measurement transfer in the inertial frame that has such orientation and magnitude, and there are possibly multiple locations may exist that represent such a background flow velocity vector. So what this means is that if we're designing an algorithm to hypothesize the location based on a flow velocity measurement, we need this algorithm to be able to handle multiple hypotheses and distinguish the correct one from the false ones. Okay. So how do we do this mathematically? All right, so this is a flow chart that represents what flow-aided navigation does in a nutshell. So this blue loop here represent a traditional direct reckoning localization methods. So this sensor is a surface mount accelerometer gyroscope sensor, and by using the sensor measurement, you can deduce the vehicle's localization, the location, but this location estimate is gonna have a growing error over time. Oops. So what flow-aided navigation add on top of the direct reckoning that most of the vehicle are already performing is to provide information from ocean general circulation models. And we use these models to generate a bunch of time-tagged background flow velocity maps so that the vehicle can reference the local background flow velocity from this map to pinpoint where the location of the robot might be. Okay. And as I mentioned, in order to do that, you need to have a flow velocity observation sensor, which is ADCP, right? So by combining the information coming from instantaneous flow observation and your model forecast, we can compare the differences between what the vehicle think the background flow velocity should be according to its estimated location and its map versus its actual background flow velocity measurement. So that error allows us to correct the long-term drifting that are induced by the direct reckoning process of the NS. Okay, so this is basically the concept of flow-aided navigation in a nutshell. So the way that we go about it is we casted this problem into a probabilistic inference problem. So where we are trying to estimate such a state vector that comprises of the position of the vehicle, the velocity, as we mentioned, that's also necessary, and also the orientation, along with a bunch of sensor biases, the bias of the accelerometer, gyroscope, and the flow velocity measurement Z. And here I have another term, which is this small scale background flow phenomena, which is not captured by the ocean prediction model. So this is necessary because the ocean prediction model can only predict large scale phenomena, but this small scale still persists in the short period that is consistent with the navigation period of the vehicle. So we wanted to keep track of that as well. Okay. So basically, we're trying to find a probability distribution of this state vector given the initial position of the robot or the initial value of this state vector, together with a bunch of sensor measurements. So the first sensor is U here. So U is basically whatever the INS tells you that encodes how the position of the robot and also orientation of the robot changes throughout the entire navigation period. Another sensor is Z, which is the relative flow velocity. So if we put the Z vector here right next to the vehicle velocity vector here, so we see that the difference between them two can be deduced from the flow map if we know the position of the vehicle. Okay, so this phi k term is basically the background flow velocity in the inertia frame. Okay. All right, so this is a high dimensional probability inference problem. So the way we went about it is that we designed an ensemble extended common filter approach. So what it does is that it uses a particle filter to sample the location or the position of the robot itself. So for P, we're using n particles to represent n different instantiations of this underwater robot position. Then each of the particles represent a copy of extended common filter. And this filter will be estimating the velocity, the orientation bias terms, and the local turbulence terms. Okay, so each of the EKF will be updated independently from each other, and the result of that will contribute to the weight that is associated with this corresponding particle. Okay, then we use this particle filter to compare which particle or which instance of the vehicle state vector is most consistent with all of the measurements provided by U and Z, and that tells us what is the position, velocity, orientation of the vehicle. Okay, so without going into the detail of the mathematics, let's take a look at how well that this works. So here is a test case where we look at the data that are collected by a surface vessel, and where the surface vessel carries an ADCP sensor that measures the relative flow velocity underneath it. And also we have a GPS track of this first surface vessel, and also the inertial navigation sensor measurement. So we are emulating an underwater vehicle using the data that are collected by this surface vessel. So this is the actual trajectory that went through during this particular segment of this large survey campaign. So here are the results that we're comparing the ground truth, which is represented by the black curve here, against the green, which is the current aided navigation approach that we're proposing here. So as you see that it does a much better job than if you are only dealing with the directing without using ocean current information. Okay, so this blue curve does slightly better than the directing. So the difference between these two is that we're assuming that we can directly measure the orientation of the vehicle, but since you do not have any correction to the velocity of the robot, so you are still diverging quite significantly from the ground truth. So this basically represents a method that allows us to achieve state-of-the-art mid-water navigation accuracy, but by using a much lower cost inertial navigation system, and also extending the navigational duration from a couple minutes to an hour, all the way to 6 hours or even more than a day. Okay, so there's a lot of promising aspects of this navigation algorithm, and we're continuously developing this approach as we speak. So one of the things that we find out during our study is that, as you can imagine, the ocean current model is not going to be capturing the actual ocean current very well. So here's a comparison between the model predicted flow velocity in the northward and eastward component against the actual flow velocity. You see that there's this gap here, right? So what that means is that we can't just 100% rely on this model prediction, right? So one of the things that we are trying to figure out is whether there's a way to allow us to update this model prediction as the vehicle navigates in the ocean, because the vehicle is actually collecting in situ observation of ocean current data. And potentially we can infuse this data into our preliminary model prediction result that can allow us to sustain the accuracy of this model prediction. Okay. So this is how we are trying to address the challenge of underwater localization in long term in mid-water column here. So I want to switch gear a little bit here to talk about the second challenge, which is efficient path planning in background flows. So here's an example where we're trying to navigate an underwater vehicle within the Gulf of Mexico flow from the initial position to the goal position. So as I mentioned, the actuation capability of the underwater robot that we're dealing with is more or less consistent with the background flow magnitude that the typical ocean possess, right? So we have to plan this trajectory of the underwater robot smartly so that we can allow the vehicle to travel from one point to another. So there has been a lot of study how to do efficient path planning in flow field. So a typical way that you can think about it is you can cast this as a constraint linear optimization problem, where you can construct a cost function that you are trying to minimize the accumulated the energy consumption, where here, for example, I'm trying to minimize the differences between the vehicle velocity x dot and the background flow velocity, where I assume that the vehicle needs to spend energy to compensate for these velocity differences. Okay, so you can do this sort of optimization simply using F-Mincon algorithm in MATLAB, but this requires you to know all of the information about the background flow, which is a very strong assumption to begin with. And secondly, this leads to a very non-convex optimization problem, because as you can see that this is the background flow is a very complex dynamical system that has a lot of local minimas. So as the problem scale increases, the search space increases significantly. Then you ended up in this curse of dimensionality, and it's very impractical to do this sort of optimization. So then the question is there anything that we can leverage from our understanding of the background flow transportation themselves that can inform us to better design our trajectory optimization? So here is a typical path planning result if we're trying to travel from this point to the goal location in a double gyro flow field. So as you can see that the vehicle is trying to follow the direction of the ocean current and trying to avoid fighting against it, right? So that makes me think that what does a passive drifter do if you are not applying any control? So as you can see that if you're not applying any control, so this drifter trajectory essentially exposes the transportation pathways that are existing in any background flow fields, right? So then the question is whether can we leverage the fact that we know the transportation property of the background flow, and can we better design this optimization trajectory so that the vehicle can leverage the background flow transport as much as possible. So this is a study that is widely explored recently. So first of all, the study was started by InexGen and Marston back in 2005, where they did an optimization of the trajectory of the underwater vehicle in the Monterey Bay area, where they compared that the optimal trajectory tends to agree with the Lagrangian coherent structure that they found in the background flow field. So the Lagrangian coherent structure is basically separations in the time-dependent systems, and they are analogous to the stable and unstable manifolds of time-independent systems. So by a following on study by Senator and Ross, they think that, okay, so if these optimal trajectories are overlapping with Lagrangian coherent structures, why don't we just control the robot so that we directly steer towards these LCS lines? And then they successfully did that, where this y curve here shows that you are trying to directly shoot to the goal. This gray curve here representing the passive trajectory, where this yellow curve here is basically trying to steer yourself towards the LCS, then deviate from the LCS when you are close enough to the goal, right? So this study that we have been carrying out is analyzing how Lagrangian coherent structure is dictating the optimal trajectory of a model Purdue control method, which is not dependent on the global understanding of the ocean current. Okay, so in order to calculate this Lagrangian coherent structure, typically you can calculate what we call the finite time Lagrangian exponent. So what that means is that if you look at two drifters that are separated by epsilon distance, if you evolve them forward in time and measure how much stretching that this separation experiences during this finite period of time, you can calculate FTLE field, and the ridge of the FTLE field will essentially give you the Lagrangian coherent structure. Okay, so without going into the detail of math, and let's look at how the model Purdue control trajectories are dependent on this Lagrangian coherent structure. So here's an example where we are trying to use model Purdue control, where we are computing the optimal trajectory in the finite period of time and trying to steer itself towards a goal. And on the right-hand side, I'm showing the underlying Lagrangian coherent structure, and where the color of this finite trajectory indicates is instantaneous energy the vehicle is spending. So where the yellow represents energy expenditure. Okay, so one finding that we realize is that when the vehicle tries to cross this unstable Lagrangian coherent structure, the instantaneous energy starts to bump up. So it's actually spending energy to cross these transportation boundaries, which is consistent with our understanding. So many studies that we've done recently were regarding trying to discover the nuances that are between the MPC parameters and the Lagrangian coherent structures. So due to time, I won't go into the details here, but we have a recent paper that is currently under review, and there's an archive copy available online. And I invite all of you to check it out if you are interested in this study. So I wanted to spend a couple of minutes talk about a third challenge before I quickly wrap up this talk. So which is the research, development, and operational challenge that are faced by underwater robotics. So I want to bring back this image that we had shown previously. So this was how we are deploying this so-called autonomous underwater vehicles back in the 50s, right? So we need to take out a crew on the surface vessel and on a nice weather day and deploy it and wait for it to come back and retrieve it. Sometimes it goes into a multiple day search, right? 60 years later, we are still doing this, right? So we still need to take a large crew out to deploy these underwater vehicles. So can we do something to address this? Because this is super costly, and super inefficient, and it has a lot of logistic demands associated with this sort of research. And it really sets up a really high barrier for underwater robotics research. So one of the recent work that we're trying to push forward is to establish this underwater robotic testbed for resident underwater vehicle, whether vehicle just lives on the seafloor. And the way to do that is to leverage this existing infrastructures where here this picture shows we have these kilonalo nearshore reef observatories where we have power and communication cable already installed on the seafloor. And if we can design a docking station that can act as a proxy for power and communication for underwater robot, then the robot can essentially live at this test bed, and we can remotely command this robot for research and development. So this is one of the directions that we're working on. And another similar concept is by combining marine renewable energy together with resident underwater robot, where we don't need a cabled power source anymore, but we do need a renewable energy platform where we can collect energy from the waves, the inner current that can power this underwater vehicle. So this is an ongoing effort funded by the Department of Energy, collaborating with Oregon State University and University of Washington, APL. Okay. So to quickly summarize what we talked about, 3 challenges that we have been working on: underwater localization, where we introduced a flow-aided navigation method, and we're also looking at how can we incorporate flow field mapping together with this flow-aided navigation. So we also talk about path planning challenges and how malleability control are dependent on Lagrangian coherent structures of the flow, and we're extending this method to multi-robot cooperative control in background flow field. And lastly, we briefly touched upon these resident underwater robotic systems. And I think in the next decade or so, there's going to be a lot of progress made in these areas. So without that, I'd like to thank my sponsors for supporting our research, and my collaborators, my students, and last but not least, you guys for hosting me for today's talk. And I'd like to hear if there's any questions.
All right, thank you, Dr. Song. Give me a round of applause.
Thank you.
So there's a couple of folks online and a couple of people here in person. We have we'll go over a little bit and have like 5 minutes for questions. I don't know if anyone in the room or online has a question to ask immediately.
So I'll ask a question. So I used to work with a bunch of ocean engineers working on this problem, and we used to talk at lunch, and I threw this out at them, and they said, "Well, yeah, that might be right." So I'd like to get your take on this. You know, the reason we have GPS today is because people had this crazy idea, about putting satellites up in space and localize on them. And no one thought that was a practical reality until there was a Cold War. And then all of a sudden we had the money to put up GPS satellites, and then 25 years later we make it an open platform, we're using it. And I would tell my ocean engineering buddies that were working on the SLAM problem, I said, well, as soon as it becomes a national defense priority, we will have underwater fixed beacons all over the place. The military's got them in certain places, but we'll have them everywhere. And so, and with the development that's going on now, don't you think we're pretty much almost there? Because the next generation warships are going to be underwater, unmanned, and they're going to be launching torpedoes and rockets and planes and drones. Don't you think in the next 10 years what's going to happen is we're going to have an underwater GPS system around the world?
Yeah, so that's a very good point, and I completely agree with your opinion on that. I think many of these challenges that we're facing can simply be addressed with the underwater GPS systems, right? If there's no logistical challenges, and so even with renewable energy progresses recently, you can install these beacons almost everywhere on the ocean surface, right? So allow these beacons to acquire power from these energy sources. Yeah, so that's definitely something I would like to see happening. And I've talked to folks that who are working on underwater cable systems, where we have these intercontinental communication cables running across our continents, carrying power and data streams. And they have been suggesting we should add repeaters on these cables so that you can do acoustic tracking and you can do ocean monitoring. And now we are looking at a huge network of underwater beacons, right? So that may very well be one version of, or at least one major portion of this global underwater GPS system, right? So, but as you mentioned, there's a lot of resistance from different parties because it has a lot of political and military reasons that why this is not existing nowadays. I think that's it's probably going to change in the future, but definitely not in the near future, right? So another thing that I like to generally touch upon is that this may not be a solution to localization on Earth or ocean in the future, right? But what if exploration on the water body on the different planets, right? So, for example, a hypothesis ocean on Europa, right? So, when you go explore those liquid body planets, you wouldn't have any sorts of localization methods, right? So the water body themselves or the liquid body themselves probably are the only reference that you can encounter with. And by the way, the Europa Ocean is hypothesized to be like 10 times deeper than the Earth Ocean. So which I think this is probably still going to be an interesting approach to investigate.
Thank you very much, and thanks for a very nice presentation. Very interesting.
Thank you.
Yeah, so we're short on time. Maybe time for one question more.
Yeah, so if there's no question, then I was going to ask you one. It's like, so it seems like with the localization part, right? How are you getting the forecast for currents updated? So like you have to resurface or somehow get that information still. Is that my correct assumption there? So
yeah, so that's a very good question. So one of the project that we're working on, funded by NSF, is trying to think about how we can incorporate this in-situ flow velocity measurement to better inform us so that we can improve on the flow map that we initially obtained before the deployment, right? So, these ocean models are simulating like in-situ measurements on a daily basis, right? You're keeping the accuracy of this prediction by incorporating these in-situ observations. When your vehicle perform this flow aided navigation, it is already having these in-situ measurements. Potentially, you can incorporate these in-situ measurements to update your flow maps as you go. So that's one thing. And another thing that we're working on is trying to extend the idea of simultaneous localization and mapping in a static environment to a fluid environment, right? So now we are talking about simultaneous flow aided navigation and flow field mapping, right? So, but now you are dealing with the dynamical system, which is infinite dimensional, right? So if you really think about it, it is a dynamics learning and localization problem. So that's something that my student Jonathan has been working on. Can we do these sort of things? Because if you just think about dynamical system regression, usually we assume that this input output data very well, right? But now we're talking about we do not know accurately this input data, but we do know that this input data are constrained, because locations cannot jump around, right? So this becomes a more fundamental theoretical problem of how can we do model regression if your input data has large noise on them. So that is something that we're currently working on. Hopefully that will address the dependency on these ocean prediction results.
right, thank you. So we're just about out of time, so we'll need to stop here. So thanks again, Dr. Song, for your time and your presentation.
Thank you very much.